So embedded software engineers or controls engineers aren't the only ones that have challenges from the testing and validation side. You know, mechanical systems themselves, in addition to embedded software, have quite a bit of challenges that are driving similar issues to them. You've got tolerances for control and for accuracy that are becoming extremely demanding. You've got new materials and drive and actuation technologies, and you can read through the list here. I won't go through all of them. But the point I want to make here is just as control engineers, control validation engineers, had to evolve their approach to testing years ago and have continued to refine that approach in order to simultaneously balance quality, budget, and timeline. Now we're getting to where the rapid advances in the technology on the mechanical world are also driving that same need for an evolution in the way we do testing of these mechanical systems. And so I've got this diagram here that'll show you what I've been seeing, how these models are being used. And so to explain it a little bit, in the blue is really the software. It's your rack. Right? It's got your processor, PXI real-time system in there, and your I/O. And then on the right, the red box there is the component being tested: transmission, differential, turbine engine, whatever you may have here. And then on the top and bottom of that red block are the drives or the motors there that are going to be providing either do the motoring or the loading of the unit under test. All right, and so today in a typical test cell or test system, you're going to have stimulus that's feeding set points to control loops in order to achieve the mechanical simulation for the unit under test. And so one thing that type of application or refinement to this type of application I'm starting to see now has been the use of these HIL or these real-time models to create a more realistic, a more accurate, a more capable test cell. And the way that what's happening there is actually the model itself, this model of the entire system. Here, let me dial in to make this a little easier. So let's say we have a powertrain system, okay, but we want to just test just one piece of that, maybe the differential. Okay, the way the model can be used then to test that differential physically in a particular vehicle configuration is to take a model that takes into account, well, what kind of transmission do we have, and what is the motor that we have, what kind of drive cycle is going to be done there, and how's the driver going to respond to that, and what are the tires, what are the friction with the road, and the actual dynamics, the inertia of the vehicle. And so all of that can be calculated in real time, so you have this simulated vehicle, but you can take that simulation and pluck out one of the models, the model of the differential in this example, and now put it physically into the real world and have it think that it is actually inside of the actual vehicle that you have specified. And so you do that by now taking from the simulation the parameters or the signals that correspond to the load or the input power that would be made to that part where it's coupled to the vehicle. And then you feed those as set points into your control loops and drives and motors to actually do the mechanical simulation. And so by doing this, it's enabling customers, and there's a couple examples over in Europe where the customer is actually able to do it's a tier 1 supplier is able to do customer specific testing. So they have a torque converter or a traction drive, and they can take the specific characteristics of one customer and perform some testing, and then also take the specific characteristics of another customer, perform testing for performance or durability and life cycle testing of that part. And they can do that, in one case, using models from the customer themselves, and in another case, it was actually building the model themselves. And so that brings me to maybe the next technology that is now just recently available on the market. And so backing up, having a plant model, if you don't have one existing in your organization that you can use, or if your customer or supplier does not have a plant model they're willing to pass on to you, then you have to invest in creating that model yourself. And building a plant model is not a small investment because typically, building a plant model, you take into account all of the systems, the physics, the electrical, the sum of all currents, the sum of all torques, and you put these equations together and you parameterize them, and then you take measurements and you get your parameters and you plug those into the equations, and eventually you get an accurate model, but you need to verify that model and continually maintain that model. Now, this is just what the cost is for models, and the return is certainly justified in many cases, especially in the embedded software case. But it's not always justifiable in the test cell or the physical testing world. And so if you're not able to acquire a model that's been built and is being maintained by someone internal or external to your organization, typically it would be hard to justify it. The return, at least today, is not there to now add a group that's going to maintain plant models for you. And there are packages out there, specifically in automotive, that provide parameterized models where you can just fill in the blanks, but they're very sophisticated, designed more for the feature implementers of software. And so other feedback I've heard is that's nice, but getting all of those parameters in there is still a very high cost, even though all the equations are already built for me and configurable. And so one new technology that is now available is a product called Dynacar. And Dynacar is a configurable or parameterized modeling environment created by Technalia. Now, if you don't know who Technalia is, Technalia is I believe it's the third largest research organization over in Europe, and they have a very heavy investment into automotive research. And they were just recently at our Worldwide Users Conference in iWeek this past August, and I got a chance to talk with them quite a bit. And these guys are really neat. They're automotive enthusiasts, and what they did, being a research organization, is they had a grant, and the purpose of their grant was to go and build a parameterized modeling environment suitable for test cell applications. And what we mean by that is they went and analyzed how you model a vehicle and a powertrain system and the lateral and longitudinal dynamics of a vehicle and all of that to see, okay, what really matters for a test cell application? What part of the, what level of fidelity really matters? And so they went and they created a model and they simplified it to the right fidelity and then created this product called Dynacar for configuring it. And the way it works is you start by selecting the type of vehicle that you're using, the architecture, the topology. Is it hybrid electric, pure electric, is it a combustion, and so on. And then based on that, you have components inside of that architecture that you're going to be configuring. So you'll have options to select in those components, which under the hood, this is all determining how the equations are going to be built for you. And then once that's done, you have windows that provide only the level of detail that is necessary for your application in regards to parameterization. So what are these actual parameters that are needed by those equations? And so after you do all that, the Dynacar environment creates this model that you need. It creates this model that you need, and then you can simply pull out of that model any part of the system that you want to physically test. And we'll talk more about that here in a little bit, but essentially you have a complete vehicle simulation and you pluck out, let's say, the torque converter from that model, and then you take the inputs and outputs to that subsystem and map them to your dynamometer so that you can do the motoring and the loading of that physical component that you need to do there. So this is a great technology. Wineman is actually their distributor here in the US, and then they, of course, provide this globally. But it's a great product that a research institute had the luxury to pour a lot of investment into with maybe a little different cost structure than most of us are under. And so there's a great value here. And so I should mention in closing on this technology, in order to finally validate the accuracy of their model, the engineers at Technalia built the worst case scenario car as far as dynamics. So they wanted to build something that would really test, was their model accurate to the real world? And so that car is actually sitting on Wineman's shop floor there. And there's also a video, I'm sure Darren has it, I think I have it on my computer as well, that shows, but they actually took that and they built a test track, again, different cost structure than most of us are under. So they built a test track out there and they drove the vehicle and they correlated the real world results of this worst case scenario with their simulated results, and then use that as they refined their equations to ensure that they could be accurate under all conditions that you could configure here. So we have that. You can take a look. They shipped that over here for our users conference. But you can also drive one of these models. So there's a demonstration in the back of the shop that is using this Dynacar model with the inertia package and the Veristine package to test a transmission. So as you drive, the model is telling the motor to put a simulated input to the transmission, and then another motor is putting a resistive load or a load simulating the road resistance. Sorry. So yeah, and so here is just an example of it's effectively what they did in the process of verifying and validating that model there, with the electric drive being the physical component.